In part 2 of the lecture, I will discuss the basics of operation of stringed instruments in regards to how sound waves are created. The strings of a stringed instrument create sound by moving the air molecules around them as they vibrate. Essentially, the same thing happens as the tuning fork hitting the air molecules. Here, the string is hitting the air molecules. Imagine the string of a guitar, for example. It is fixed at both ends. This is the string in its relaxed state. But if the string is pulled and released, let's say it will have similar shape or such shape, and then it's going to vibrate in both directions. Of course, about the equilibrium. And so that's going to cause the air molecules that get into contact with it to move away. And then we get these compressions and rarefactions of the molecules, and that's the sound generated by this string. So each string is fixed at both ends. The waves that are created in the string interfere with each other and create these standing wave patterns. So this is a single wave shown here. It propagates like so. It gets to the other fixed end, reflects from there, goes back. And so this wave pattern here remains unchanged over time. Therefore, this is a standing wave pattern. So for stringed instruments, when the strings are pulled, standing wave patterns are formed. One important piece of information to keep in mind is that a string can accommodate multiple waves with different frequencies at the same time. So here we have only a single wave with one frequency or its own frequency shown, but on that same string there can be more than one wave existing at the same time, so they will all work together to produce an actual melody, if you will, by combining the different frequencies together in, meaningful way. So the collection of all frequencies that can exist on the string is called harmonic series. The harmonic series is the collection of all frequencies that can exist on a string. The frequencies of those waves from the harmonic series are also known as harmonics. Harmonics are the frequencies of the waves in the harmonic series. The harmonic series will be different for different lengths of strings. So even if we have two strings made from the exact same material with the exact same diameter, if the lengths are different, then different harmonic series can be excited on those two strings. There is a relationship between the length of a string and the wavelength or frequency of the wave that can be excited on such string. Let's look into that in a little bit more detail. Let's see how the first harmonic is produced on a string that is fixed at both ends. Let's set the problem up by considering a string that has a length capital L. The wave with the longest wavelength and the smallest frequency that can be excited on this string and forms a standing wave pattern is called the fundamental wave, and the frequency of that fundamental wave is called the fundamental frequency or the first harmonic. So the first harmonic is the wave with the longest wavelength lambda and the smallest frequency f that can be excited on the string. So let's see what that looks like. When I say that the first harmonic is the wave with the longest wavelength lambda and the smallest frequency f, that means that we can only have full number of wavelengths or whole number of wavelengths that it fits on the entire string. We cannot have fractional numbers of wavelengths fitting on the string, because then there will be no a standing wave pattern on that string. And so here is the fundamental wave shown on the string. We have half of the wavelength is the length of this branch, and then the second branch here is the other half of the wavelength. And so those two 1/2 wavelengths are fit on the physical length of the string. So these are wavelengths, so the length of the wave. This is the physical length of the string. So to help you visualize a little bit better, let's change the drawing a little bit to be able to relate it to the drawing that I did in the previous video lecture with waves on a rope. Let's take this branch and unfold it to the right. When that is done, then we get another length of the string L, and then this branch is right here. Okay, so from our discussion of what a wavelength looks like, well, here is it. We start here, and then we go all the way to here, and then after that, if we had more, the picture will repeat itself. The pattern will repeat itself. So this is one full wavelength. Therefore, half of it is half of the wavelength, and the other half, which is this part, is the other half of the wavelength. So the wave starts at this end of the string, propagates to the right, hits the other fixed end, and then reflects and propagates to the left. The two waves interfere with each other on the string, and they form this standing wave pattern. So I now can essentially find the relationship between the physical length of the string and the length of the wave excited on the string. From this drawing, we can see that I can fit half of a wavelength on the length of the string L. So then my relationship between the two is that half of the wavelength is equal to the length of the string, or from here I can say that lambda 1 is equal to 2 times L. And so lambda 1 is the wavelength of the fundamental wave. Now let's find out what the first harmonic frequency is in terms of the length of the string. First, remember that the speed with which the wave propagates in the string is related to the wavelength and the frequency of the wave. And this relationship is given by V is equal to lambda times F. So from here, the frequency will be the speed of the wave on the string divided by the wavelength of the wave. So I already have an expression for the wavelength of the first harmonic, and so the frequency F1, the first harmonic frequency, is going to be equal to V divided by 2 times L. And here V is the speed of the wave on the string. So the two relationships to remember here are the one for the wavelength and the one for the frequency. Now let's see what the second harmonic looks like. So for the second harmonic, again, we have a string with length L. The next wave that can fit on the string will have two wavelengths that look like so. The wave starts from the left fixed end, propagates towards the right fixed end, it reflects from there, and then propagates towards the left fixed end. We have 3 node points and 2 antinodes. And so based on this standing wave pattern, each branch is equal to 1/2 of the wavelength. And the direction of propagation is like so. So now here we see that we have 1/2 plus 1/2 wavelengths that fit on the length of the string. So then the relationship between the wavelength of the wave and the physical length of the string is lambda divided by 2 plus lambda divided by 2 is equal to L, from where we get that 2 times lambda divided by 2 is equal to L, or in other words, lambda 2 is equal to L. And so lambda 2 is the wavelength of the second harmonic. Now let's determine the second harmonic frequency. Here I'm going to again use the relationship between the speed of the wave on the string, the wavelength, and the frequency of the wave. So for the second harmonic, the speed will be equal to the wavelength of the second harmonic times the frequency of the second harmonic. So then the second harmonic frequency F2 is equal to V divided by lambda 2. But I know that lambda 2 is equal to L. For the purpose of being able to generalize the formula for any harmonic frequency, I'm going to write the relationship as 2 times V divided by 2 times L. So as you can see, if the 2's are cancelled, then we get that F2 is equal to V divided by L, which is consistent with what we get here if I substitute lambda 2 with L. And so the second harmonic, F2, is equal to 2V divided by 2L. Let's do the third harmonic, and then I'll be able to generalize the expressions for any harmonic that can be excited on this string. The third harmonic is a wave that has 2 wavelengths fitting on the length of the string. So here is the first wavelength, here is the second wavelength, and here is the third wavelength. So again, each branch is equal to half of the wavelength of the wave. And the wave propagates like so on the string. So the lower branches are also half of the wavelength. So now, by counting, we see that we have 3 half wavelengths that fit on the length of the string, like that. So then the relationship is 3 times lambda divided by 2 is equal to L. And from here, the wavelength of the third harmonic, lambda 3, is simply 2 times L divided by 3. Now let's do the third harmonic frequency. For the third harmonic frequency, again, we use the relationship between the speed of the wave, the wavelength, and the frequency of the wave. So V is equal to lambda 3 times F3. So the third harmonic frequency, F3, is equal to V divided by lambda 3. Or this is equal to 3 times V divided by 2L. So the third harmonic frequency is 3V divided by 2L. Okay, so now I can derive a general expression for the wavelengths and for the frequencies of the harmonics that can be excited on this string. So here is a summarized list of the formulas or the relationships for a wavelength and frequency for each harmonic. So notice that for the first harmonic, the wavelength is equal to 2 times the length of the string. For the second harmonic, the wavelength is equal to 2 times the length of the string divided by 2. For the third harmonic, the wavelength is equal to 2 times the length of the string divided by 3. So with each consequent harmonic, the wavelength essentially is divided by the harmonic number. So then I can write a general formula for the wavelengths of the harmonic series. And this formula is that the wavelength of the nth harmonic is equal to 2 times the length of the string divided by n, where n is equal to 1, 2, 3, 4, and so on and so forth. So for each harmonic, you simply will replace n with the number of the harmonic. So for the first harmonic, n1 is equal to 2l divided by 1, so that's this one. For the second harmonic, n2 is 2l divided by 2, that is this one. For the third harmonic, for n equal 3, lambda 3 is equal to 2l divided by 3, so that is this one, and so on and so forth. Now let's look at the frequencies. The first harmonic frequency is equal to the speed of the wave divided by twice the length of the string. For the second harmonic frequency, we have twice the speed of the wave divided by twice the length of the string. For the third harmonic, we have 3 times the speed of the wave divided by twice the length of the string. So essentially, every consequent harmonic frequency is equal to the speed of the wave divided by 2 times the length of the string multiplied by the number of the harmonic. So then I can write a general formula for any harmonic frequency, and that is that the harmonic frequency is equal to n times the speed of the wave divided by 2 times the length of the string, and here n is again equal to 1, 2, 3, 4, so on and so forth. So for the first harmonic, n equal to 1, f1 is equal to v divided by 2l. So that's this one. For the second harmonic, n is equal to 2, so f2 is equal to 2 times v divided by 2l. That is this one. For the third harmonic, we have f3 equals to 3 times v divided by 2 times l. So that is this one. So this is the general formula for any frequency in the harmonic series.